Yeah. Hello. As Olivia said, I'll be talking about how to use GIT to relate toric mirror constructions, which is a slightly different title than I had originally planned, but I decided to slightly pivot my message. So first, I'm going to kind of motivate the problem and set it up a little bit. Then I'm going to talk about the methods I use, so variations of GIT. The third part is my actual result that I've been working on. And the fourth part is just, if we have time, I'm going to talk about some like more general bits and bobs. So if we have a Calabi-Yau manifold X, there's two kinds of structures that we want to look at it. The first bit is the symplectic structure, which is known as the A side. It's like Gromov-Witten invariants, Lagrangian submanifolds, sphere counting, curve counting, all these kind of things of symplectic topology. And the second bit is the complex structure, the B side. So that would be like period integrals, coherent sheaves, deformations, and that's more the algebraic geometry side, which I'm more comfortable with. Mirror symmetry is roughly a duality between these two structures. So if we have one Calabi-Yau manifold V, which has these two structures, then mirror symmetry asserts that there should be a second Calabi-Yau W, which is dual to it, so that these structures are mirrored. In other words, the symplectic structure on one is like the complex structure on the other, and vice versa. This is, in that sense, not very precise because it's a phenomenon first observed in physics, and how to make that precise is a bit debated, I would say. So there's different things one could consider. One could consider like the topology on it. That gives you one line of inquiry that you calculate the Euler characteristics and say like, oh, the Euler characteristic of one should be -1 to the dimension of the other. Or you can look at deformations and say, oh, the deformations on one side should correspond to deformations on the other. And what I'm mostly working in is homological mirror symmetry, introduced by Kontsevich. And there we categorize these two structures by two things. On the B side, we use the bounded derived category of coherent sheaves. The objects are cochain complexes, which are quasi-isomorphic to bounded derived complexes of coherent sheaves. That's the algebra geometry side of it. The other side, the Fukaya category, I know less about. That's Lagrangian submanifolds, and it should contain all the symplectic information. So Kontsevich conjectured that if you have two dual Calabi-Yaus, V and W, then you should get equivalences that the derived category on one side is equivalent to the Fukaya category on the other side, and vice versa. In particular, this means that if you have two mirrors to the same Calabi-Yau, because you might get two candidates, depending on what conditions you used beforehand. Like if you say, oh, I cared about the topology, I cared about the cohomology, you might get different ways to construct such mirrors. These things are known as mirror constructions, and there is a myriad out there. So depending what criterion you looked at, you might get two different mirror candidates, W and W prime. And ideally, if Kontsevich's mirror conjecture holds as is, you should get an equivalence between the derived categories. So I'm going to present a way to use variations of geometric invariant theory to prove such derived equivalences, and I am going to do it based on two examples. One of them is the well-studied Batyrev-Borisov example, which is the classic toric geometry polar duality thing that many might have seen. And the other is the Libgober-Teitelbaum construction, which was a paper coming out in '94, where they, well, I'm going to present it later, but they just proposed a mirror candidate, and it's more or less of a unique case in it. They don't give a construction of it. The research is based on many papers by Isik, Schiepmann, Hirano, Siegel, Favero-Kelly, and Herbst-Bacher. And yeah, let's start by looking at the Libgober-Teitelbaum construction. So we consider a complete intersection of two cubics in P5. These cubics are very general. This is how they look like. It's, yeah, one of the nicest things to write down if you want. The proposed mirror uses the same two polynomials Q1 and Q2, but we look at their intersection in a quotient space. that quotient space is P5 by a finite group, which I will show in the next slide. And they use the topological evidence I talked about earlier to say like, oh, we look at the two Euler characteristics and we want them flipped. So we take the complete intersection, we resolve it, and that should be a mirror candidate. They then provide evidence. And here's the group they come up with. It's some automorphism group. And yeah, it's technically a rather nice mirror in some sense, because it's the same complete intersection we had before, just in a quotient space. If all mirror symmetry was that, we just take appropriate quotients, that would be great. So the only question is, okay, so this nice mirror, how does it relate to the one we kind of systematically got from the Batyrev-Borisov construction? Because we know that they're different. My result is based on homological mirror symmetry, which is saying that these two mirror constructions are derived equivalent. And that's what it looks like. Well, we don't take the entire pencil of possible polynomials. We exclude a couple of cases, but otherwise, in the stacky world, we have a derived equivalence between the two mirror constructions. Right. But more important than the result is kind of how we get there. So this picture is a picture I want you to keep in mind. It kind of symbolizes the ansatz I have. In some sense, we will have, well, not some sense, we will have a fan, and we will have two chambers of that fan, sigma p and sigma q. It's going to be a secondary fan, so each chamber corresponds to some triangulation, which I will describe in a bit. And the idea is that parts of that triangulation will correspond to a vector bundle and therefore to a complete intersection by looking at these sections. We can relate that the derived category of the complete intersection to a singular category associated to the entire chamber. We can then use some wall crossing on the fan to get to a singular category of another chamber. And then we can play the game backwards and restrict again to some other vector bundle and get the derived category. So the rough idea to show derived equivalences is to take these intermediate steps via this bigger fan. The setup, we considered some G equivariant vector bundle on X, and we denote by that the zero locus of a G invariant section. The pairing with S will then give you a global function on the dual vector bundle. We consider the zero section of this pairing and the fiberwise dilation action on the torus. And all that we'll be doing is GIT on this dual vector bundle, which is what this fan is. So let's talk a bit about what we mean by GIT. So if we think about toric varieties and the Cox construction, remember that we can represent varieties as an affine space where we cut out an exceptional locus and we quotient by a group. That is what we want GIT quotients to be in general. So we take some affine space X, we remove a special set of points Z, and we quotient by a group acting on the subspace, on the space. The way that you find out which set to remove, though, is we look at characters of the group. So the main difference between all of these GIT quotients will be what do we remove. And if we look at characters of the group S, we can assign some stability conditions on them, because each character will correspond to some linearization of a line bundle. And this gives you different GIT quotients. The question is, okay, if I pick two characters, do we always remove different sets? Do we sometimes remove the same set? And yeah, so yeah, these stability conditions define some semi-stable loci. This is what we will be removing. But sometimes these characters share the same affine patch. And now, if you think of the parameter space of the character group, so the parameter space of linearizations, so you kind of write down all your characters in a space, then you play the game of saying, okay, if two characters give me the same affine patch, I group them together. That is by proven to be a GKZ fan. It's called the secondary fan of our toric variety that we started with. And each chamber of it will correspond to a different GIT quotient. And that is the fan that we considered earlier with the chambers sigma P and sigma Q. So now that we know what the chambers are, I talked about some categories associated to them. So we start again with X a variety and G an algebraic group acting on X. And now we define the singular category. So an object of the bounded derived category is called perfect if it's locally quasi-isomorphic to a bounded complex of G equivariant vector bundles. This gives you a full subcategory of perfect objects. So we can take the Verdier quotient, and that is the singular category. There is a reason we call it the category singularity, at least in my mind, is due to a nice result of Orloff's, which basically claims that if you have an open immersion from a space U to X, such that the singular locus is contained in the image of U, then you can, the restriction of the singular category is equivalence of categories. So in some sense, all the information of the singular category is really located in the locus of singularities. The rest of the space is, in some sense, noise, as I would like to think about it. So now we need to figure out the four equivalences we had in the earlier slide. I'm going to quickly bring it up again. So you want to go from derived to singular category. And that's what this result by Isaac, Shipman, and Hirano does. If we have an exact Koszul complex on S, then we have an equivalence of categories between the derived category of the quotient Z by G and of Y by G times torus, which is, so Z quotient by G is like the complete intersection, that orbifold, and Y is the entire associated to the entire chamber of the fan. In Favera-Kelly's paper, they kind of reformulate this a bit. So we have an algebraic variety V with a G cross GM action and an open subset, which is equivalently isomorphic to Y, such that U contains the singular locus. Then we get pretty much the same equivalence, except that now it's not for Y the entire thing, but just for V already, for the algebraic variety. So we now want to kind of use these equivalence of categories and apply them to a GIT situation. So we start with some affine space, which has n plus t coordinates. The first n coordinates are the xi, the next t coordinates are the uj. And I like to think of the uj as bundle coordinates and the xi of actual, like the coordinates of the actual underlying space. We denote by t the standard torus, and we consider some subgroup S of it, where S hat is the connected component which contains the identity. Then we will study the GIT quotients for the actions of S hat on X, and technically what we're doing is we study the associated Landau-Ginzburg models. So one way, as an example, what to do would be to take your favorite toric variety and construct a vector bundle on it. That way, you introduce more coordinates, which will then become the uj, and they're the bundle coordinates. And that's also what we will be doing. Because we're talking about Landau-Ginzburg models, which are assigned to the chambers, we need a superpotential. That superpotential very easily is just obtained from the pairing that we talked about earlier. And we can write it as a sum of bundle coordinate times function. We then consider the zero locus of that entire superpotential in the affine variety. And we can also look like, what does this actually look like restricted to each patch in the chamber? So that's how you get these affine bits UP, which is the zero locus of the superpotential, but restricted to your chamber. An example, if we take X to be P2, we consider the vector bundle O of 3, then the dual vector bundle is O of -3. So on the left, we just construct the vector bundle for O3 in the way that Coxwell-Schenk describes to us how to construct a vector bundle. And if you take the dual vector bundle, you obtain the figure on the right. You take a cone over these 3 points, and each point in the dual corresponds to a global function, which is what I've done here. So like the top bit -1 to 1 corresponds to uy cubed, you have ux cubed, you have uz cubed, and you have everything in between. So a section of O3 is a point in the dual cone, and you can get the superpotential just by u times that monomial or polynomial that you take out of the points that you've chosen. Now we come to the bit where the variations of GAT becomes useful, because right now we found some results that allow us to equate the derived categories to some singular categories, but we don't know yet how to go from one singular category to another. And that's this little result here, which says like, okay, as long as the action is quasi-Calabi-Yau, then you get an equivalence between the singular categories from one chamber to the next. And that's a very powerful result. To apply it, we will.
Aimeric,
yeah.
Who HW? Who was that citation?
Oh, sorry, Herbst-Walther.
Oh, Herbst-Walther. Okay.
Sorry.
Herbst-Walther.
Yes, I pronounced it probably the German way.
Cool. Oh, sorry. Thanks.
So to make this a little bit more applicable, all of these things, because we want something handheld, really a result that we can use, that we don't need to check more abstract conditions. We want something we can check algebraically. So for each chamber in the secondary fan, we know by basic toric geometry, I think it's chapter 14 or 15 of Coxwell-Schenk, that it corresponds to regular triangulation of a certain set of points, just nu1 to nu(n) plus t. In practice, these points are, if you write down your fan of your toric variety that you want to build a secondary fan on, and each of these rays can be identified with a point by just taking the primitive ray generator, then these ray generators will end up being the points that you triangulate. So you get n of those that way, and then you get the t bundle coordinates when you construct a vector bundle. So the two ideals you associated to them is you take your regular triangulation, you look at the simplices in it, and for each simplex, the first ideal, the IP, is all those variables associated to the points that you have not used in your simplex. I'm going to give an example in a second. And the JP is exactly the same, except that this time you require all the bundle coordinates to be used in the simplex. So here's an example of a very small triangulation. We have 5 points. 4 of them are associated to xi's. And the one in the middle of the square is a bundle coordinate. Then we have 2 simplices on the left, which is x1, x2, x3. So we do not use x4 and u1. So that's one of our 2 generators of the ideal. And the other generator, we have x2, x3, x4 as these things spanning the simplex. To span it, we don't use u1 or x1. So u1, x1 is the other monomial in the spanning set. There is, however, no simplex which uses all the ui. In this case, there is only one. So J is empty. On the right-hand side, we have 4 simplices, 4 triangles. And the first triangle, x1, x2, u1, we don't use x3 and x4. So I made a typo. x3, x4 should be one of the ideals in there. x2, x4, u1 is another triangle. So x1, x3 should be a generator, and so on. And we also see all of these triangles use all of the u's. So actually, I and j correspond to the same ideal. We have the same generators because we use the same simplices. Now, if we take this second ideal j and we remove it, that gives us a sub piece of the affine patch. We also note that because by construction, all the simplices we used to build JP had all of the bundle coordinates U. So technically, it's a subideal of Cx1 to xn. And that gives us another affine open subset of AN, which we denote by VPX. We can build a toric stack by taking the quotient via the group we started with. And in fact, we now can view if we remember the superpotential was the sum of some uj, fj, and the sum of the fj's, we can now see that as a section of this VP. So we have constructed a vector bundle. And that will give us a complete intersection. And if we now look back to the picture, in some sense, the points in the middle will be the bundle coordinates, and we kind of pick the points corresponding to sections so that, like, oh, if we take these points in the dual cone, then that is a section, because this is for the dual vector bundle EV, then that's a section of E. So we have now kind of constructed a complete intersection of the functions corresponding to these points. And then we can use the categorical results. There's one little catch. So the algebraic condition I talked about that we would like to just be able to check as opposed to all the abstract stuff is this ideal containment condition. So we need I to be contained in the radical of J and the partial W. If this containment holds, then the singular category of your chamber corresponds to the derived category of the complete intersection in that chamber. I'd like to make a little bit of sense of that to myself sometimes by thinking, okay, so the I will be what gives me the YP. It gives me like the variety of the chamber, because the GRT quotient is affine space minus 0 locus of I quotiented by the group. And J is related to the complete intersection on the right side, whereas partial W will give me my singular locus, because singular loci are computed by using the partials. As a little corollary of that, if we combine all the previous results, we get exactly the chain of equivalences. So if S is quasi-Calabi-Yau and JP and JQ are non-zero, then if we have the ideal containment conditions for two chambers, then we can actually find a derived equivalences between the categories of coherent sheaves of these complete intersections, simply by introducing these middle steps of the singular categories, which were in the picture. So that's the powerful results that I wanted to really talk about. And in my research, I have used this result on the two constructions I talked about earlier, the Batyrev-Borisov and the Libgober-Teitelbaum construction. So let me tell you about that next. So back to the problem motivating us. How exactly do we use it on those two constructions? It's quite clear that Batyrev-Borisov is toric, so it shouldn't be a problem to set up the GRT problem. It's a toric variety. We just take the secondary fan, everything's fine, we're happy. But Libgober-Teitelbaum did not give us a toric variety, they gave us a quotient. So the first thing to do is we need to kind of translate this into toric geometry. So what we've done, and oh, typos. We first found a fan for like the variety where the complete intersection lives in, P5 quotiented by G81. And we've done that by just constructing the vector bundle O minus 3, O minus 3 is a toric variety. We take the dual cone, and points in the dual correspond to global functions. So we just pick the points corresponding to the superpotential. The superpotential should be the sum of the two polynomials we started with, Q1 and Q2. This will give us, those were 8 monomials, so we should have 8 points. If we now consider these 8 points to be rays, then we get a vector bundle. And a section of this vector bundle is just the direct sum of the two polynomials we started with. These are all like small toric computations to do. There's nothing too heavy inside it. And if we quotient by the bundle coordinates, well, that's just some toric geometry. Oh, we quotient by the arrays. That's fine. It's compatible. So we get something toric, and we get a fan that you can compute actually corresponds to the quotient space P5 by G81. But cool. So now we have two toric varieties, two toric things. How do we actually compare them? I computed the Batyrev-Borisov mirror, and similar to above, built a vector bundle on it such that the two functions that I wrote in the theorem, P1 and P2, which really look like Q1, Q2, just with some added bits, is a section. We then get 14 points by doing the same procedure of going into the dual, picking points corresponding to the function. And the crucial idea here is we find a chamber in this secondary fan of this second vector bundle of Batyrev-Borisov that partially compactifies the variety that corresponds, the vector bundle that corresponds to Libgober-Teitelbaum. Because if we think back about the picture, we have the small green, the small red triangle, and we kind of want a chamber such that, oh, the small red triangle really lives in a smaller space that is partially compactified. The small green triangle is what Batyrev-Borisov is. And yeah, I just found some triangulations associated to these chambers corresponding to the Batyrev-Borisov vector bundle and to partial compactification of the Libgober-Teitelbaum vector bundle. And then we can just compute the associated ideals. A small computation is just some straightforward algebra, allows us to check the conditions of the corollary, and we get a derived equivalence, which then proves the main theorem. Okay. So now the question is, how can one use that? Because the Libgober-Teitelbaum thing is probably more heuristically that they found the variety by trying a lot of things out. But if I were to start with some variety and I wanted to find an adequate mirror, how would I maybe go about it? Is there like a nicer way to do it? Because Batyrev-Borisov gets computationally harder very quickly, whereas just by looking at the size of the fan we needed for the toric varieties, Libgober-Teitelbaum seemed easier. It seemed like a nicer way to construct a mirror. It's also a more intuitive way. Hey, we take a quotient. So I've tried to just say, okay, if I use the results I have, can I just directly generalize it to other dimensions? So the first very obvious thing to do would be to literally just straight down write out the polynomials, but with higher exponents and with more variables. So I set out with the idea, we take these two polynomials which are here, and we want to try and find a Libgober-Teitelbaum style mirror candidate to their complete intersection. So if we just do the analogous complications, we get some quotient space, which is P2n-1 quotiented by the finite group, and the finite group has this form. It's, again, we just constructed the vector bundle, we took the dual, we picked the points, we took the quotient, and this would make sense. It's great. In n equals 2, everything works out perfectly. The proof follows. We get a complete intersection in P3, and we get an analogous result. I'm happy. The problem was trying to go to higher dimensions. Turns out the variety is singular. That is a problem because the algebra breaks down. And that also makes sense because the singular category is not that nicely well behaved. We have a lot of problems in the VGIT. Not good. This seemed like a dead end, and I tried for several months to fix it. And after consulting with my advisor, we're kind of like, wait, what do we usually do when there's singularities? If there's singularities in normal algebraic geometry, we just try to blow things up. We try to resolve. And there is an analog to resolving, but in categories, so categorical resolutions. That should help us, and indeed it does. So what is a categorical resolution? If we have a derived category D, and if D tilde is a homotopy category of a homologically smooth and proper pre-triangulated DG category, then a resolution is just a pair of exact functors going back and forth, such that one of the functors is from the homotopy category to the derived category started with. The other one is from the subcategory of perfect objects to this homotopy category D tilde, and we want some adjointness properties and some natural morphisms between those functors. That is a derived category, a categorical resolution, and we would like to construct one of those. And here is the result in preparation, which is exactly saying like, oh, I picked the two polynomials which I thought would be great generalizations, and I take the pencil over them as long as we stay away from a couple of critical points. Then we have this group I described earlier that leaves the hypersurfaces untouched. And we take a Batyrev-Borisov mirror, and fundamentally the Batyrev-Borisov mirror categorically resolves the complete intersection we get from these two. Which in some sense would mean that constructing the mirror this way by taking this group quotient contains all the necessary information. So Batyrev-Borisov resolves it. I don't quite have a mirror because I don't quite have the derived thing, but I have something similar enough. So the proof is based on results of Favero and Kelly, and I, for the life of me, could not get it to compile, so I had to include a picture of the diagram I made in another document. What you do is you take your derived category of the complete intersection. This Zn is the Batyrev-Borisov one, Yn is the one from the Libgober-Teitelbaum style mirrors, and you construct a pair of functors to something called the absolute derived category of the Landau-Ginzburg model. So each chamber is a corresponds to the Landau-Ginzburg model, and GIT is nice. So these absolute derived categories under a couple of conditions are equivalent, and you should get a pair of functors to the complete intersections. Previously, that was just a singular category is equivalent to derived category. Now it's absolute category has a pair of functors to the derived category. There is a lot of conditions to be checked, like homological smoothness needs to be checked somewhere, so we need to check some compactness and stuff. But for Batyrev-Borisov on the right side, everything's nice, everything's perfect. We get this pair of functors is actually an equivalence, and everything's fun. On the left side, a lot more algebra has to be done, but in this specific example, we get a categorical resolution, and yeah, we follow through the chain of arrows, and we get a categorical resolution of Batyrev-Borisov and the Libgober-Teitelbaum construction. So the steps in the proof are fundamentally the same as before. We need two chambers in a common GKZ fan, partially compactifying my two complete intersections. We need to show that the absolute derived categories are equivalent that correspond to these two chambers. And we need to show that on the right-hand side, oh, that should be a Zn. Everything is nice. We get an equivalence to the Batyrev-Borisov mirror. And then we need to show on the left-hand side that we actually have enough smoothness and properness that this entire thing is, that this pair of functors becomes a categorical resolution. Yeah, I've gone a bit faster than I wanted to. I'm sorry about that, but I thank you for your attention.